I see this as the title summarizing the core concept. We're using ElasticNet regression with cross-validation to choose the best model. ElasticNetCV is a tool in scikit-learn, a Python library, that helps us do this automatically. I'm given a dataset with lots of features, some of which are closely related. The challenge is to build a good model that generalizes well to new data, avoiding overfitting. Meaning the model works well only on the data it's trained on, not new data. The _koa_ attribute stores the numbers that represent how much each feature influences the model's predictions. After ElasticNetCV tries different settings, it gives me the coefficients from the model that performed best. During cross-validation, I won't automatically get the lowest mean squared error, MSE, just by using ElasticNet. While ElasticNet often does better than Lasso or Ridge alone, there's no guarantee. The best performing model really depends on the specific data I'm working with. MSE measures how much the model's predictions differ from the actual values. Lower is better. I'm using 5-fold cross-validation. That means the data is split into 5 groups. The model is trained on 4 groups and tested on the remaining group, and this process is repeated 5 times, each time using a different group as the test set. This helps to evaluate how well different combinations of alpha, how strong the regularization is, an L1_ ratio, how much of each type of regularization to use, perform. This is a subheading, not needing elaboration here. These are also subheadings, not needing elaboration here. This is a multiple choice question assessing understanding of ElasticNetCV in scikit-learn. I'm testing your knowledge of how ElasticNetCV works. I'm asking you to evaluate 4 statements about the model created using ElasticNetCV. Each statement describes a different aspect of the model's behavior or characteristics. This statement is true. I explicitly set _CV equals 5 meaning the model will use 5-fold cross-validation. This technique divides the dataset into 5 parts. 4 parts are used to train the model, and the remaining part is used to test. I repeat this process 5 times, each time using a different part of the data for testing. The results are then averaged. This statement is also correct. The ElasticNetCV model automatically searches for the optimal alpha, regularization strength, and L1_ ratio to minimize error during cross-validation. I am letting the algorithm find the best settings from the range provided. This is true. The _koa_ attribute will store the final feature weights. These weights will correspond to the hyperparameter combination, alpha and L1_ ratio, determined to be optimal via the cross-validation process I've implemented. This statement is false. While ElasticNet often performs better than Lasso or Ridge because it combines their strengths, I can't guarantee that it will always have a lower mean squared error, MSE. The best model depends entirely on the data used. I'm using ElasticNetCV, a powerful tool from scikit-learn that cleverly finds the best combination of regularization strengths, alpha, and the balance between L1 and L2 regularization, L1_ ratio, for my linear regression model. It's like having a smart assistant that automatically tunes the model for optimal performance. It's super efficient. Here, I specify 5-fold cross-validation, _CV equals 5 meaning I'll split my data into 5 parts. I'll train my model on 4 parts and test it on the remaining part, repeating this process 5 times, each time using a different test set. This gives a more robust estimate of performance. I also tell ElasticNetCV to explore different mixtures of L1, Lasso, and L2, Ridge, regularization, using L1_ ratio values of 0.1, 0.5, and 0.9. These values represent the proportion of L1 regularization. 0.1 is mostly Ridge, 0.9 is mostly Lasso, and 0.5 is a 50-50 mix. This is the process I'm using to avoid overfitting. I'm systematically testing several model configurations across different data subsets to pick the best performing model for unseen data. It's a more accurate reflection of model capabilities than training and testing on just a single split of the data. After cross-validation, ElasticNetCV automatically picks the best values for alpha, regularization strength, and L1_ ratio. the ones which resulted in the lowest cross-validated error. It's like it tries out various settings and picks the one which works best. Pretty clever, huh? I obtain a final model. This model uses the optimal alpha and L1 ratio values. I can access its feature coefficients, the _coa attribute, to see how much each feature contributes to the model's prediction. These are the coefficients from the model that performed best during cross-validation. Pretty straightforward. I'm using ElasticNet, a type of regression that combines lasso and ridge regression techniques to find the best balance between fitting data and avoiding overfitting. It's a powerful tool for dealing with lots of features, some of which might be related to each other. Think of it as a smart blend of two great approaches. I've set up my ElasticNet model using 5-fold cross-validation, CV equals 5, so I get a robust estimate of how well it generalizes to unseen data. I'm also testing different ratios of lasso, L1, and ridge, L2, penalties, 0.1, 0.5 and 0.9. This means I'm experimenting to find the optimal mix of L1 and L2 regularization that works best for my dataset, represents how much weight is given to lasso, L1, penalty. To avoid overfitting, I'm using cross-validation. I'm splitting my data into 5 groups and training the model on 4 and testing on 1. And doing this until each group has served as the testing group. This gives me a more reliable measure of how well the model will perform on new, unseen data. It helps me avoid the trap of a model that only performs well on the specific data it was trained on, overfitting. The ElasticNetCV automatically searches for the best values, alpha and L1 ratio, that minimize error using cross-validation. Think of it as a built-in optimization process which finds the optimal combination of these hyperparameters. After searching for the best settings, ElasticNetCV produces a final model. The _coa attribute holds the weights, coefficients, assigned to each feature in that final, best-performing model. These coefficients show how much each feature influences the final prediction. Higher values indicate a greater contribution. I'm using ElasticNet with cross-validation, ElasticNetCV. It's a powerful tool that automatically tunes hyperparameters, the settings that control the model's behavior, to find the best fit for your data. The CV part means it uses cross-validation to avoid overfitting. I have a dataset where some features are strongly related. This can cause problems for simple linear models, making them unstable and prone to overfitting. ElasticNetCV helps me address this by combining different types of regularization. My goal is to build a model that performs well not just on my training data, but also on new, unseen data. This means I want good generalization capability, avoiding overfitting. ElasticNetCV is a great approach because it helps with that. I have many features in the dataset. Many features can lead to overfitting, but ElasticNetCV can cleverly deal with that. I'm using ElasticNetCV with 5-fold cross-validation, CV equals 5 . This means I'll split my data into 5 parts, training the model on 4 parts and testing on the remaining 1 part, rotating which part serves as test data. I'm also exploring different balance points between L1 and L2 regularization using the L1 ratio parameter, testing values 0.1, 0.5, and 0.9. L1 is lasso regularization and L2 is ridge regularization. ElasticNetCV does automatic hyperparameter tuning. It automatically searches for the best values for alpha the overall regularization strength, and L1 ratio the balance between L1 and L2 regularization, from the ranges I provide. I use 5-fold cross-validation to estimate how well my model will generalize to new data. It's a robust way to avoid overfitting and get a more reliable performance estimate. The model is trained 5 times. After the automatic search, I get the best performing model. That's the best model based on the combination of hyperparameters found by the cross-validation process. The _coa attribute of the model holds the feature weights of the best model found after the automatic search and 5-fold cross-validation. These coefficients tell me how much each feature contributes to the predictions. I'm using ElasticNet with cross-validation, ElasticNetCV, to find the best model. This method automatically tunes the model's parameters to achieve optimal performance. I have a dataset with many features, some of which are closely related. I want a model that works well on unseen data and isn't overly sensitive to my specific training data. That's why I'm using regularization techniques to avoid overfitting. To evaluate my model's performance, I will use 5-fold cross-validation. That means, I will split my data into 5 groups. I'll train the model on 4 groups and test it on the remaining one. I'll repeat this process until each group has been used for testing. This gives me a more robust estimate of how well the model generalizes. The ElasticNetCV algorithm will automatically find the best values for ALPHA, regularization strength, and the balance between L1 and L2 regularization. Think of ALPHA as controlling the overall amount of regularization and as controlling the mix of L1, lasso, and L2, ridge, penalties. After cross-validation, I'll have a model with the best settings and its coefficients, the values that determine the model's predictions, which will be stored in the COEF attribute. It will represent the model that performed best during cross-validation. Yes, that's the main advantage of using ElasticNetCV. It automatically searches for the best combination of these hyperparameters during the cross-validation process. Exactly. I explicitly specified 5-fold cross-validation using "CV equals 5". This ensures a reliable evaluation of the model. Nope. While ElasticNet often performs well, there's no guarantee it will always outperform lasso or ridge. The best model depends on the specific data. Absolutely. The "COA_" attribute will contain the coefficients for the model that achieve the lowest error during cross-validation. I see this as a blueprint for the ElasticNet model with cross-validation. It's the overall structure of how we'll build and evaluate our model. Think of it as the big picture. This is the information we're feeding into our model. The features, the independent variables, and the target, the dependent variable we want to predict. This is the raw material for the model. This is the specific machine learning algorithm I'm using. ElasticNet combines lasso and ridge regression, using both L1 and L2 regularization. It's a powerful tool for finding the optimal balance between model simplicity and accuracy. Here, I'm setting up cross-validation. CV equals 5 means I'll split the data into 5 parts, training on 4 and testing on 1, and rotating until every part has been a test set. This helps prevent overfitting. L1_ratio controls the mix of L1 and L2 regularization. I'm testing different mixtures, 0.1, 0.5, 0.9. I'm searching for the best values for alpha, which controls the overall strength of regularization, and L1_ratio, the lasso, ridge mix. This is like fine-tuning the model for optimal performance. After trying different combinations, I'll pick the best one, the one that gives the lowest error during cross-validation. This is the optimal model based on my data. The final output is the best model, identified through cross-validation, and its associated feature coefficients. COA_. These coefficients tell us how each feature influences the prediction. These are the 2 types of regression models that ElasticNet combines. Lasso uses L1 regularization. It shrinks some coefficients to exactly 0. And ridge uses L2 regularization. Shrinks all coefficients but doesn't make them 0. This is the quiz question. I need to evaluate the truthfulness of the multiple choice answers based on my understanding of ElasticNetCV. This is the first option for the quiz question. It claims that the algorithm automatically chooses the best regularization parameters. It is true. This is the second option for the quiz question. This is the option related to the cross-validation technique used. It is true. This is the third option for the quiz question. This option claims MSE of ElasticNet will be lower than lasso or ridge. This is false. This is the fourth option for the quiz question. This option is related to the coefficients that the model returns. It is true.